the equilibrium constant for this reaction, Kw. And at 25 degrees Celsius, we said that Kw is equal to 1 times 10 to the minus 14. And using an ice table, we were able to calculate that the equilibrium concentrations of H3O plus and OH minus, when it's only water in the beaker, are equal, it's neutral, and that their concentration is equal to the square root of the Kw, 1 times 10 to the minus 7 moles per liter. But when we add acid or a base, so in addition, adding additional H3O plus or OH minus to the water, we essentially alter this equilibrium. Okay, so if we think back to Le Chatelier's principle, if we add more H3O plus to the to this reaction in equilibrium, which way does the reaction shift? Shifts towards the reactants. Okay, so if we add H3O plus, the reaction needs to shift towards the reactants to regain equilibrium. So the way that the equilibrium is affected when H3O plus is added is that it shifts towards the reactant. So what does that mean about the OH minus concentration? What's going to happen to that? Increase or decrease? Stay the same. So if we're shifting the equilibrium to the reactants, that means the concentration of OH minus has to decrease. Okay? At equilibrium. So that means it's going to become less than 1 times 10 to the minus 7. Okay, at equilibrium, it's 1 times 10 to the minus 7. If we add acids, that shifts the equilibrium to the reactants. The concentration of the other product goes down. That's Le Chatelier's principle. And so based simply on that, and the fact that we're adding an acid to the water, we end up with an acidic solution. Okay? If we were to do the opposite and add OH minus to the equilibrium, again we shift towards the reactants, the concentration of the H3O plus would decrease below that of 1 times 10 to the minus 7. So let's look at an example of adding HCl, which is a strong acid, to water. We know that when we put HCl in solution, it completely dissociates, so single arrow towards the products, into H plus or H3O plus and Cl minus. Okay, I'm using H plus and H3O plus interchangeably here, just simply based on how I've written out HCl. Okay. If we wanted to include how HCl reacts specifically with water, now you can actually see where the H3O plus comes in. Okay, like so. Okay. So again, strong acids, they completely dissociate. Complete dissociation. Okay. We're going to see here in the next few slides what's going to happen with a weak acid, where we're going to get only partial dissociation of the H plus from the rest of the acid. Okay. So if we start with 0.1 molar HCl in solution, how much H3O plus is formed? So what does that mean? Essentially what we're going to be doing is looking at this equilibrium. 2H2O in equilibrium with H3O plus OH minus. Okay. If we put 0.1 molar HCl in solution, we get 0.1 molar H3O plus, right? So that's going to completely dissociate. The HCl completely dissociates. So for every 1 mole of HCl, you get 1 mole of H3O plus. Okay, that's based on. And so if we want to look now at the equilibrium of the autoionization of water, we can set up an ice table where we have an initial concentration of H3O plus at 0.1 molar. We don't need to worry about the concentration of water in this equilibrium because water is a liquid. Okay. We said that the equilibrium when we add a strong acid to water is going to shift towards the reactants, which means the concentration of products are going to decrease by some amount, and that some amount is X. So at equilibrium, the concentration of H3O plus is 0.1 minus X, and the concentration of OH minus is X. Okay. Everyone okay up there? Yeah.
You're not starting with the HCl, you're just putting it as it's not in the initial equation.
It's not in this initial equation because I wanted to see how I'm specifically showing you how the concentration, the contribution of autoionization of water is affected by the addition of acid. So we're going to do this sort of a two-step thing. Okay, first we're going to look at the concentrations of H3O plus and OH minus in the autoionization. Okay. And then we're also going to show you what you already know, which is how to calculate the pH of a solution of 0.1 molar acid. Okay. We all did that probably for practice for years. So now I'm going to kind of show you the equilibrium portion of that. So we said on the previous slides that the concentration of hydroxide, OH minus, is going to be less than 1 times 10 to the minus 7. Right? Because we've taken our equilibrium, we're shifting it towards the reactants, and there's going to be fewer products. So based on that, we know that X is less than 1 times 10 to the minus 7. Now we could actually solve this. You can use our Kw, our equilibrium constant. We can actually go down here. We'll do this. Kw is 1 times 10 to the minus 14. Minus 14. And that's equal to the concentration of H3O plus times the concentration of OH minus. We know at equilibrium for this reaction, H3O plus is going to be 0.1 minus X, and the equilibrium concentration of OH minus is going to be X. So if we solve for X, we have a quadratic, because we're going to get 1 times 10 to the minus 14 equals 0.10 X. So multiplying here, minus X squared. Everyone okay with that? Yeah. Oh, you're right. It is. Yeah. Okay. Does anyone want to solve the quadratic for me? I don't want to do it. It's got a program in there, calculator. But you do that, right? No one's like jumping us. So if you don't recall, or you don't have your calculator programmed, this is the equation for solving the quadratic. X is going to be equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. And the a is equal to the coefficient in front of the squared factor. In this case is 1. B is what's in front of the x, in this case 0.10. And c is the other portion, and I plus. This is going to be minus 1 times 10 to the minus 17. Minus 14, wow, okay. Because we get everything written on one side. So we'll have x squared plus 0.1 x minus 1 times 10 to the minus 14 equals 0. Okay, what do we get for x? One times 10 to the minus 13. That sounds correct. Really small number. Okay. So in that case, the concentration of OH minus is going to be 1 times 10 to the minus 13. And the concentration of H3O plus, going back to our ice table, 0.1 minus X is 0.1 minus 1 times 10 to the minus 13. Okay. Everyone okay with that math? Yes.
As the negative x portion.
I knew that was coming up.
There, why shouldn't it be the negative, or why isn't it that negative x is less than 1 times 10 to the negative 7 if negative x is the concentration of x?
We're not going to end up with a negative concentration. This should be x, but we are subtracting that value in the change line. No, wait. One of the answers was a negative, right? Is that correct? It doesn't matter. Okay. Yes, so this is going to be equal to the value of x. And these are what we're going to end up with. Okay. Was that your question? Yeah. So in that equilibrium, we have to have some amount x, right, of the OH minus. And it's coming from that dissociation, which I guess makes it positive. But because we're switching, let's just go with this for now, and I'll come up with a better answer for you. Okay, but what I want you to see, the important part here, because you're not actually going to need to do these equations like this necessarily. All right, but what I want you to see is how small that value of x is. Okay, tiny, right? But we already knew that because when we put HCl in solution, we had 0.1 molar of it, correct? And we know that when we have a strong acid, we can calculate the pH as minus the log of the H3O plus concentration. Okay. Which means the pH is equal to minus the log of 0.1. And that gives us 1.00. Oh, move some pages here. And what does that make the POH? At 25 degrees Celsius, we can solve for POH. Do 14 minus the pH, 13. We could get those same values from the ice table that we calculated. OH minus, we calculated 1 times 10 to the minus 13. Take minus the log of that, you're going to get 13 for the POH. And what is the, what happens when you subtract 1 times 10 to the minus 13 from 0.1? You end up with approximately 0.1, right? So what the point of this slide is that when we add a strong acid to water, the autoionization, the H2O in equilibrium with H3O plus OH minus, is negligible. So we don't actually need to go through this whole process, and we don't want to anyways, obviously I can tell from the reactions I'm getting, that when we have a strong acid, we can get the concentration of H3O plus, pH equals minus the log of that concentration. Okay? That's great. Autoionization contributes very little. There is one example where that's not true. Well, there's a couple examples, but let's do one more calculation. Not on this, it's not exactly on this slide. Let's say we add 1 times 10 to the minus 8 molar HCl. We add HCl till we get a 1 times 10 to the minus 8 molar concentration in solution. So we have 1 times 10 to the minus 8 molar HCl in solution. What is the pH? (25 degrees Celsius). What do we get? Please yell out the wrong answer. Yeah, Garrett? You get an 8. Thank you. If we did pH equals minus the log of 1 times 10 to the minus 8, it says that the pH is 8. Ah. We'll put an exclamation point there, okay? But we've added HCl to solution, right? So in that case, because the concentration that we add is so small, the autoionization of water does make it. So we would have to add in, do this same business over here that we didn't want to do with the strong acid at a high concentration. The ice table with the autoionization of water. Okay. We have to go through that whole thing to figure out the actual concentration of a 1 times 10 to the minus 8 molar HCl solution. That says it's basic. We know it can't be basic. And so we would go through the process to figure out what it is. Yes?
Is there a specific concentration
Yes. So the question is, at what concentration? Like, what's our lowest concentration before we have to consider autoionization of water? And that's going to be about 1 times 10 to the minus 6. Getting lower than that, you're going to have to start taking into account autoionization. I don't think we're going to ask you that kind of question. Okay. But it is interesting to see. So, like the numbers, right? You just play with the math, but you can't. You have to think about the chemistry too. Yes.
Okay, so to clarify.
Yeah.
With the 8.
Yes.
That's like, you can't do that.
That's correct. So that is not the actual pH. Okay. If we went through, I think it's been a while since I've actually done the calculation. I think we end up with a pH of 6.98. I could go through and add that in later to the notes. That might be kind of tough for me. But yeah, it is not. Questions? Okay. Just a note on this slide that the change line in this equilibrium is going to be plus X for H3O plus and OH minus. And so we just need to kind of correct that here, plus X for the equilibrium line. We did this already. Okay, well here's our statement. That was your question. For strong acids and bases, the autoionization of water is negligible at concentrations greater than 1 times 10 to the minus 6 molar. Okay, and I can't think of a question where we would actually do autoionization, but that doesn't mean we're not going to have you do equilibrium. It's just not going to usually show up that way. Okay. Questions before I move on to a strong base? So barium hydroxide is a strong base. It has a solubility of 0.1077 moles per liter at 25 degrees Celsius. And let's say we dissolve that many moles of the barium hydroxide in 1 liter of water, 25 C. Essentially, we're making a saturated solution. We're going to go back to our chapter 13 concept here. Let's calculate the concentration of hydroxide and then determine the pH. Okay. Keep in mind when we take barium hydroxide and put it in solution, we form barium 2 plus and 2 hydroxide ions. Okay? The stoichiometry matters here. So what I'm going to have you do is work with your neighbor, calculate first the hydroxide ion concentration, then calculate the pOH, and then the pH, and then we'll do them all together. So work with your neighbor. All right. So there's one sort of tricky part to this question. Okay? We're given the number of moles of barium hydroxide that were dissolved in 1 liter of water. So we were told that we have 0.1077 moles of barium hydroxide per liter, but we don't want to know, we don't care about the concentration of barium hydroxide, we care about the concentration only of hydroxide. Okay? So we need to use this stoichiometry to determine the number of moles or the moles per liter of hydroxide in solution. So we use the stoichiometry or the formula for barium hydroxide. So I'm going to use some dimensional analysis. For every 1 mole of barium hydroxide, we get 2 moles of hydroxide ion. And so that allows our moles of barium hydroxide to cancel, and we are going to be left with moles of OH minus per liter of solution. Okay? And we end up with, so this is 2 times 0.1077, which is 0.2154. Okay? If you didn't catch that, completely understand, this is an easy place to make a mistake. There are a number of strong bases that have the formula cation 2OH. So watch for those and know that and keep track of what concentration you're given. Okay, are you giving concentration of OH minus, or are you giving concentration of the salt? Okay, so based on that, we're going to have 0.2154 moles per liter of OH minus. We can take minus the log of 0.2154 to find the pOH, and we'll get 0.667. Actually, 6667. We can write that. And so finding the pH is going to be 14 minus 0.6667, and we get 13.3332. Okay. Questions on that? Okay, so what happens if we then add 500 mils of water to that solution? How does the pH change? What pH do we end up with? So really the only thing we need to worry about now is the concentration. That's what's changing. We're going to be diluting the sample. So instead of having, we had 0.2154 moles of OH minus per liter. We now are going to have we multiply by 1 liter. This is 0.2154 moles. We're going to have 0.2154 moles per 1.5 liters, which is 0.1436 moles per liter. This way. You can find the pOH, what I didn't write down, minus the log of 0.1436. pH equals 14 minus the log. And I get 13.1572. So I wanted to show this calculation because we increased the volume, we diluted the solution by a significant amount. But the pH doesn't change very much. 13.3 to 13.2 essentially. And that's typical of what we see with strong acids and bases, right? If they're a strong acid and base, they're going to have a really low or a really high pH, respectively. Okay. Questions on any of this? All right. All right, so I'll have you work on this one. Here we're going to have a mixture of acids, 0.2 moles per liter HCl. We're going to take 50 milliliters of that, and we're going to add it to 125 milliliters of 0.1 mole per liter HI. Right? You have a new total volume. Okay, figure out the total number of moles of H3O plus over the total volume to get the concentration of H3O plus, and then find the pH. I'll let you work on that for a couple minutes. All right. Okay, so important thing to know here is that the acids aren't going to react with each other. Essentially, they both completely dissociate in solution. The concentrations of H plus or H3O plus are additive. And so the first thing we'll want to do is find the moles of H plus from HI and HCl. So from HCl, we have 0.020 moles of H plus per liter, okay? I'm making a leap here, all right, in my notes. So instead of showing you that HCl completely dissociates to form, so for every 1 mole of HCl, we get 1 mole of H plus. I'm sort of leaping through that step. So we know then if we have 0.02 moles of HCl, we're going to have 0.02 moles of H+. And we have, we're going to put 50 milliliters of this solution into a container. So if we multiply by the volume, 0.05 liters, we're going to end up with the moles of H+. 1 times 10 to the minus 3 moles of H+ contributed from the HCl. Same thing then from HI. Okay, we're going to have 0.01 moles per liter of HI. For every 1 HI, we get 1 H+. So I'll have 0.010 mole of H+ per liter. We have 125 milliliters of that, or 0.125 liters. And we end up with 1.25 times 10 to the minus 3 moles of H+. Okay, everyone okay with that? And now we add them together to give us the total moles in solution when we combine these two acids. And we'll have 2.25 times 10 to the minus 3 moles of H+. What's our total volume? Yeah. 175 milliliters, or 0.175 liters. So if we take our moles, divide by the total volume, we end up with an H+ concentration of 0.0129 moles per liter. Okay, and from there, finding the pH, we take minus the log. And we'll end up with 1.889. Yes. Yeah, you could do N1V1. But we need to make sure we add the moles of H+. So if you did that, you would do it, yes. I think you would get the same answer. Yeah. Other things? Yeah.
Are we going to do one of these where it's like a strong acid related to it? Do you want to shift or check right out the balance before you do first?
2-to-1 ratio, like adding
Yeah, it's like it's really strong
possibly.
acid.
Yeah, possibly. Yeah. What we won't do is have you do a strong acid plus a weak acid. Yeah. Sort of. Yeah. Other things? All right. Okay, so let's talk about weak acids. We'll do some sort of general things here. Number one thing, weak acids don't completely ionize in solution. That means they don't completely dissociate in solution. So we're going to have an equilibrium. So with our strong acids, we wrote our strong acid arrow. Now we're using our equilibrium arrow when we have a weak acid. Okay. This is acetic acid. You're going to see this one frequently in examples. Okay, so this is our acid. In this case, water is going to act as a base in this equilibrium, which means H3O plus is the conjugate acid, and CH3COO minus is the conjugate base. that's referred to as acetate ion. So you might see that come up. Okay. Now, I don't know about you, but I'm lazy, right? And so I don't like writing out all of the formulas for weak acids and weak bases. So there is a way that we can represent an acid that makes every weak acid problem, almost every weak acid problem, look exactly the same. And this is really nice because when we are solving equilibrium with weak acids and weak bases, if the formula all look the same, then essentially we're solving the same problem with just different numbers. Okay. So typically what I will do for a weak acid is write the formula HA. This is a monoprotic weak acid, meaning it has one proton. I will, if we react this with water, we're going to form its conjugate base, A minus, and H3O plus. So that is a very generalized weak acid equilibrium. And this is the one I will essentially use every time. HA plus H2O in equilibrium with A minus and H3O plus. And then in writing that, it makes writing our equilibrium expression also very easy. It will look the same every time. Our equilibrium constant is going to be equal to the concentration of products over reactants. And again, we have water in this equilibrium, which is a liquid, so we're going to ignore that in the equilibrium constant expression. So that means we'll have K is equal to the concentration of A minus times H3O plus divided by the concentration of HA. And this is given a special symbol for its equilibrium constant K, K of A. So A for acid. So remember that chart I had you look at? I told you last time to look at that chart. Maybe you've seen it, maybe you haven't since then. From that chart that shows the strength of acids, weak acids and strong acids and all of that, we would look at that chart and be able to see that H3O plus is a stronger acid than acetic acid. Okay? Which means that the equilibrium is going to shift towards the reactants. Okay? And what that means then is that our equilibrium constant, Ka, is going to be small, less than 1. And you're going to see that with most weak acids. We're going to have really small Ka values. And we can, in fact, calculate the amount of ionization that a weak acid will undergo. For if we take a 0.1 molar solution of acetic acid, which is vinegar, by the way, usually what you have at home is 3% acetic acid. I don't know what that is in molarity. You can figure that out. But 0.1 molar acetic acid only has about 1% of acetate, the conjugate base present in solution. So that ionization does not occur to a great extent. And so if we look at that pictorially, here on the left-hand side, we're going to have a strong acid. And so in solution, we're not going to see any HA. Okay, we could represent a strong acid with HA. All we see are A minus and H3O plus. But with a weak acid, we're going to have HA We're going to have H3O plus, and we're going to have some A minus present in solution. There's a lot more HA here, 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 than there are A minus and H3O plus. All right. Questions on any of that? All right. Everyone feeling Friday? Yeah. Friday after an exam. It's brutal. Let's be done.